welcome back. In the last lecture towards the end we saw that there are two energy levels which are created in spin half nuclei by applying a magnetic field, and I mentioned that the number of molecules which are in the ground state are higher than the number of molecules which are in the upper state, excited state. Now the question is, how do we know that? What decides whether molecules are more here or equal or higher in the upper state? So there is this famous law which is called as the Boltzmann law, which is what we will now look at, and that helps us to decide or tell what is the ratio or what is the number of how many molecules are in the ground state and how many are in the upper state. So let us go through that equation. So let us say we have half the number of molecules which are in the ground state, let us call them as n half, and the molecules which are in the excited state we will call them as minus half, because remember beta state is higher energy and the plus half alpha state is lower energy. So total number of nuclei or sample molecules is n alpha plus n beta. So the Boltzmann law is given like this, the Boltzmann formula. It says that the number of molecules in the upper state, if you divide it by the lower state, the ratio, if you take the ratio of number of molecules, it is given by e raised to the power minus delta E over kT, where delta E is the energy difference between the two levels. This is the energy gap which I showed in the last slide. So what is this energy gap? Now energy gap is created because of the magnetic field. That means if I have a very high energy gap, that this number will go down. If you can see this, if I put higher value of delta E, e raised to minus delta E by kT will come down, which means the number of molecules in the upper state will go down because this ratio will decrease. So this ratio therefore is dependent on this value of delta E. The other parameter which it depends on is this temperature, because K is a constant. So if I decrease the temperature, you can see here in this, if you put the formula, that lower temperature, this the number of molecules, the ratio will actually again go down, which means the number of molecules in the ground state will become much more than the number of molecules in the upper excited state. So lower the temperature, the ratio is lower, meaning less number of molecules are in the upper. If the limit, in the limit that you take T equal to 0, that is 0 degree Kelvin, remember this is in Kelvins not in Celsius units. So if you take temperature as 0, you will see that the entire number of molecules are in the. So this actually is essentially the Boltzmann formula, which tells us that the energy that depends on basically the difference in the energy gap, and that is this energy gap which I just now showed in the previous slide is given by this formula gamma h into B0. So it depends on gamma. So the bigger the gamma, higher the gamma, the energy gap will be higher, and similarly higher the magnetic field you apply, it will be higher. So the magnetic field and gamma control the energy gap between the upper state and the lower state. So this is something which we use to play, which are we NMR spectroscopists use this to play around to increase the sensitivity or decrease and so on, which we will see as we go on. But remember, look at this ratio here, it is not that it is really a big difference. The two upper state and ground state are almost equal. You see it is just 1.00001 10 to the power minus 5 more than in the ground state is little bit more than the upper state. Okay, so this is the ratio of upper state to ground state, is opposite of what I said, but that ratio is only little more than 1, which basically means that the populations are almost equal between the upper and lower, but not exactly equal, there is still more in the ground state. And that is the reason why we say that NMR is very low in sensitivity. And where is the sensitivity coming from? Why is the sensitivity dependent on this? It depends on the difference in the number of molecules between the ground state and the upper state. So the difference, if it is very small, you can see here the difference is, they are almost equal. So the difference is very close to 0, and if the difference is 0, exactly 0, of course the sensitivity is 0, but if the difference is very small, the sensitivity is also very small. So that is one of the reason why there has been a lot of push in that NMR technology to improve this, increase this delta E. Remember, this is something not in our hands, this is a constant for proton, carbon, nitrogen and any nucleus, but what can be changed is this B0. So if I increase the B0 going to higher and higher magnetic field, I can increase delta E, and if I can increase delta E, I can improve this ratio, I can make it little bit better than 1. I mean little bit better than what is it right now at room temperature. So therefore, there has been a lot of technological push to go for higher magnetic field, and very especially for biomolecules like proteins and nucleic acids, it is very critical that we go to very high magnetic field. The reason being the sensitivity is a very key factor. In biomolecules, the sensitivity is always low, because the sample is a big molecule, the proteins are big molecules, their concentrations are very low. We normally do not get very high concentration samples, because they either aggregate or the availability is low. So, under such conditions we have to go for as high sensitivity as possible, and that the only way to do that is, one of the ways how to do that is go to higher magnetic fields. So, as we go along we will see how this magnetic field affects the sensitivity. So, therefore, this is what is now in this particular slide. You can see here that the difference between the molecules, now here there is an exaggerated difference, it is not actually what we normally see, but this is just as a schematic drawing. So, you can see there are more number of molecules in this alpha state, that is a lower energy state compared to the higher energy. Now, how do I increase the sensitivity? I can increase sensitivity if I reduce the number of molecules here shown here, and I increase the number of molecules in the ground state. So, what am I doing therefore? I am actually increasing the difference in the population. So, what is important for us is this difference. So, if I keep decreasing this side and I keep increasing on this side, my sensitivity will keep increasing. But I cannot do that simply by changing some parameter. I have to actually change either the magnetic field, which is depending on this gap, that means I have to make this gap more and more, or I have to lower the temperature. So, typically what happens in NMR is temperature is something we do not go below for biomolecules, especially we do not go below 0 degrees Celsius, because that is the freezing point for water, which is the most common solvent in biomolecules. So, therefore, going below 0 degree Celsius, which is 273 Kelvin, is not an option. So, mainly the temperature is ruled out as an option to increase the sensitivity. The only option now is to increase the magnetic field. So, that is why, as I said, magnetic field, higher the magnetic field, better the sensitivity is. So, that is essentially what is coming from the Boltzmann law, that the population difference depends on the magnetic field and the temperature. So, this is shown here again, that if you actually, now let us look at the temperature parameter, how temperature affects. So, you can see that here if I increase the delta E and keep the temperature constant. So, I am keeping this constant, but I am increasing this magnetic field. If I do that, I increase this gap. When I increase this gap, according to this formula, my number of molecules in the n beta, that is upper state, will go down, because delta E is, here it should be delta E by kT. So, this is what is shown here, delta E by kT. So, if I increase the temperature or increase the magnetic field, this term comes down, I mean this whole term becomes less, which means n beta is less. So, the ratio becomes less. So, there are more molecules here than the upper molecule. So, this is one of the very popular ways to increase sensitivity in NMR, and especially for biomolecules, which we will need to, which we will see as we go along. So, these are the three different ways you can actually increase the sensitivity. We have seen that if you can go to higher gamma, which is essentially going to a nucleus which has higher gamma value, the highest gamma is for hydrogen proton, and this is why hydrogen is the most popular nucleus, and carbon is not very high, it has 4 times less gamma than proton. So, carbon sensitivity is much less than proton. So, again for biomolecules there are different ways to improve that. One option is to use, we will come to that, that is called heteronuclear NMR methods, where you transfer the energy from hydrogen to carbon, that is one way. Or you can actually make the carbon enriched, the molecule completely enriched with C13, because C13 has two problems. One is it has lower gamma compared to proton, and its abundance, C13 abundance is also very low, it is only 1%. So, at least we can increase the abundance of C13 by enriching the molecule, and that comes under the purview of isotope labeling, and that will help us to improve. A second way to, or option to increase the sensitivity, we already saw, that is magnetic field, which increases the gap, and all of them actually increase the gap. So, therefore, they increase the mole population difference, and lowering the temperature. This, as I said, is more or less not so possible for biomolecules. The reason being, we take biomolecules normally in water most of the time, and water samples freeze at 0 degree Celsius. So, obviously you can't study a frozen sample molecule. So, that is why we have to work normally at room temperature. We can actually increase the concentration of the sample, that is another way to improve the sensitivity, but the concentration cannot be again increased too much for biomolecules because they start aggregating, they start denaturing or degrading. So, therefore, there is a limit on the concentration what we can do for biomolecules. So, as we will see a few slides down, further other parameters for sensitivity which is important. Now, let us look at now a little bit deeper into these concepts of NMR. So, as I said, we have already seen this, the picture on the right is familiar now. We applied a magnetic field and that magnetic field resulted in an energy gap, and we apply a energy radiation, and that radiation is given by this frequency, and that takes the molecule from a ground state to the excited state. And this is the what is known as a quantum mechanical picture. Why do we call it as quantum mechanical picture? Because remember, when we talk about when we only in quantum mechanics we talk about discrete energy levels. So, these discrete energy levels meaning they are not continuous, there is a finite gap, and that discreteness has come because of applying the quantum mechanical rules. Now, NMR is a beautiful technique which not only can be understood in this way, it can also be understood in a purely a simple hand waving vector picture, or what is called as classical picture. Okay. So, this is something which is very unique to NMR. Normally, when we talk about spectroscopy, it comes under quantum mechanical way of describing it, but NMR can also be understood in a very little in a hand waving, I would say, or a vector model. So, let us see how we can do that, how we can understand NMR in this manner, that is in a classical manner. So, in classical picture, what we say is that the NMR, this is something which I will not derive in this part, and this is was done in the previous course, and also it is available in textbooks. So, the result is that a nucleus which is spinning, now it has two types of motion. One is the spin, which already we called it as half h cross, or half or integer or I value, I was basically half for hydrogen. So, that I we can think of it as a spinning nucleus. Now, the nucleus also starts moving around this magnetic field, and that is called as a Larmor precession. That happens because of some physical principles, and that the nucleus, now we can say if it is this molecule, that is the nucleus hydrogen is in alpha state, it will precess like this, and if it is beta state, it will precess in the anti-clockwise or in the opposite manner. Okay. So, that is essentially the two states which are depicted here. Now, this precession means it is like a molecule going around this axis needs, we have to give a frequency value to this, because this has a particular speed at which it is moving, and that frequency is given by omega equal to gamma into B 0. This is omega is basically the frequency or angular frequency is equal to gamma, which is a gyromagnetic, and B 0 is a magnetic field. So, what it says is that this movement, that is this precession, is faster, much faster if I increase the B 0, and this precession is very slow if I reduce the B 0. So, this precession is basically dependent on the magnetic field, and what is interesting is this frequency value, which is essentially gamma B 0 of the precession, is also coming here. You can see this is the same as the energy needed for it to be excited. So, there is now you can see some connection coming out between the classical way of looking at this NMR phenomenon and a quantum mechanical way. We actually will now exploit this connection to explain or to understand the phenomenon of resonance. So, as we go on. So, what is important to very important note is that this precessional frequency, that is just the frequency of the angular frequency of the movement, is the same as the frequency which is needed for energy for the molecule to jump from ground state to energy state. So, we can see this frequency omega is now given in some units, which is megahertz, because the magnetic field is also is in the units of Tesla, and if you plug in the values, something which you can see here has been done. So, if you let us say your magnetic field is 7 Tesla, and if you put this value and gamma value here, gamma value is something which is available in all the textbooks. So, you should try this yourself, put this, take the value of gamma for hydrogen for example, multiply that with the magnetic field which is in Tesla, you will get this value, that is 300 megahertz. So, this is the frequency which you always we mention of the spectrometer, 300 megahertz spectrometer, 500 megahertz spectrometer and so on. So, that value is coming from the magnetic field. So, you can see now for 11.75 Tesla it is 500 megahertz, and if you go to very high magnetic field 21 Tesla it is 900 megahertz. So, when again biomolecules we deal with this kind of magnetic fields or this kind of magnetic fields, and for small molecules we look at smaller magnetic field. So, now how do we, when I say it is a huge magnetic field, how do I know it is huge? It is actually comparison with earth magnetic field. So, if you look at earth magnetic field, which is the one which is normally present, which means all around us, it is 0.5 Gauss, and you see here 1 Gauss 10 to the power 4 Gauss is 1 Tesla, 10,000 Gauss is 1 Tesla. Not only that, we have 21 Tesla as a magnetic field. So, 21 into 10,000. So, you see it is a huge very high magnetic field compared to what is normally regular in the earth magnetic field. So, therefore, we have to be very careful about these magnets, and they are very specially built. They are not simple magnets, they are superconducting magnets, and there are a lot of important things behind the construction of magnet, which we may not be able to see in this course, because this course mainly focuses on application, and the hardware NMR aspects of this course of the magnets have been discussed in the previous course. So, I would recommend to look at those slides or those videos for understanding the magnets. Now, let us come back to this classical picture here. So, now as I said, NMR can be understood both in classical way as well as in quantum mechanical way. For a easier understanding, this picture is much better. So, now let us say that this is alpha state, which is pointing in the up direction, and this is a beta state in the negative direction, and they are precessing with a Larmor precision, and that frequency, as I said, is omega I naught. We use the word 0 here is because the main magnetic field which is applied along the z axis is normally denoted as B0. So, B0, and therefore, omega is omega 0. Okay. So, if B0 becomes B1, then omega will become omega 1. So, this 0 which is shown here is follows this 0 here. Now, we consider only 1 or 2 nuclei hydrogen, but in a sample it is not like that. In a sample you have a large number of nuclei, because if you for example consider water, you will have 10 to the power 20th Avogadro number of molecules of water, and each water molecule has 2 protons. So, you see the protons will be now really a huge number, and each proton is shown here like an arrow. So, instead of writing this kind of a picture which is difficult to write for a large number of molecules, I am showing this as a single arrow. So, one arrow represents one hydrogen atom or nucleus. So, you can see now one thing which happens is that these hydrogen atoms are all precessing around this, but they are not together, they are actually spread out, meaning they are not going, they are all moving in the same direction, but not moving together, they are spread out. This is a random difference, that is there is no specific particular difference between the gap. So, the entire set of atoms or nuclei are spread out along the cone, that is for all those hydrogen atoms or nucleus which are in the alpha state. Remember, there are always some nuclei in the upper state also according to the Boltzmann law, and those are represented here by downward pointing arrows, and these arrows also are actually precessing or moving around in this direction, but again they are randomly spread out in the cone. So, the angle of this each of these arrows, if you look at each of these arrows with respect to the z value, z axis is same, because they are in a cone, but they are not moving together, they are randomly phased. This is a very popular term which we call as random phase approximation, which we will come to as we go along. So, you can see here that at equilibrium meaning I have taken this sample, I have taken a sample, put it in the magnetic field, and that magnetic field creates a difference. The molecules are now distributed up and down, and those who are in the up state are all in the randomized cone the direction, and all in the ground state are also in the randomized direction. Now, what I can do is I can simply add the vectors in the different components. For example, I can take a component of this vector, which is where the mouse is pointing along x axis, I can take a component of this vector along y axis, I can take a component of this along z axis. So, this is called components of a vector. Similarly, I can take a component of this vector on the opposite side along x axis and along y axis and along z axis. So, if you notice between these two, what has happened is the component along the x and this component along this x, they are opposite. So, they will cancel each other. Similarly, if you take the component of this vector along y, will cancel the component of this vector along minus y. So, they will again cancel, but they both of them are pointing in the z axis, the z component are in the same direction. So, they will add up. Okay. So, this is what happens. What happens is for the down facing spins, their x and y are all cancelled, but their all z components will add up. Same thing will go on this side. Here also for each vector, if I take a component along x axis, there will be somebody on the opposite side which will cancel that in the x axis. Similarly, if I take along y axis, some component of that will cancel along y axis. So, therefore, all the molecules on the up state also have 0 components along x and y, because they are all cancelling each other, but their z component will start adding up, because the z is in all the same direction, they are all pointing up. So, I have now a z component which is pointing in the plus z axis for the alpha spins, and I have a minus z component adding up for all the beta spins. So, now the alpha and beta starts cancelling, but they will not cancel exactly, because according to the Boltzmann law, we know that alpha molecules in the alpha state, the number of molecules are higher than beta state, even though the difference is very small, but the difference is surely not 0. So, therefore, if I now take the z axis component of the alpha spins and cancel with the z minus z of the beta, they will still be a finite or non-zero plus z axis component remaining, because the number of molecules in the alpha state is higher than number of molecules in the beta state at equilibrium room temperature. So, this is what we use the word in NMR, magnetization. This is the net magnetic moment or magnetization of the molecule in the sample, because now this, you see, this vector captures the entire spin magnetic moments, because all of them are spread like this, and we have actually combined them and then shown that x and y are all cancelled, but the y remains, z remains in this direction. So, entire NMR now operates on this particular net magnetic moment or magnetization. If the population were equal, then this would have been 0, and therefore, nothing, no NMR would have been possible. But the fact that populations are not equal is what we are exploiting here, and we end up with this net magnetization. Now, this is what we actually use for carrying out all the NMR experiments. So, let us see that how we do that, how do we carry out the experiment. So, this is what is shown here. This is again the two pictures, classical picture and quantum. Remember, NMR is the same technique, we are looking from two different perspectives, two different views, but finally we have to get the same result. So, we have this picture and this picture have to coincide or merge or be consistent with each other. So, if you look at this picture first, what I need is an energy which will excite the molecule from ground level to the excited level. This is what I use the word resonance. For that, I need to apply a radiation which matches this energy gap, and that radiation should now be equal to this energy, because that is the energy gap here, and therefore, I use omega gamma b 0, this omega gamma b 0, and they match, molecules will be excited. Now, how do I understand this whole process in the classical way, and this is shown here. I do the same thing, I actually have a spin which is moving in this direction, which is the Larmor precession, and I apply this radiation which is the same with the same frequency as the precessional frequency. So, if the precessional frequency matches this energy of radiation, then this molecule will be excited and will go from alpha state to beta state. Similarly, beta will also be excited, it will go to alpha state, but the entire, as I said, depends on how much is the population difference. So, this is shown here in the pictorial format. This is the radiation which is being passed to the sample, and you can see this radiation can be visualized in a circle also. Remember, any electromagnetic wave can also be picturized in a circular manner. So, this has what is called the amplitude, this length is amplitude, and it is a phase. A phase essentially is how much it is away from this y axis. So, now if I apply a radiation which is on the xy plane, so I take this circle, this circular radiation, I put it in the xy plane. So, look at this picture here, it is actually happening in the xy direction. is not in the z direction, but the molecule is moving in the z. So, if you look at this picture here, this is also an xy plane, because the molecule is precessing in the around the z axis. So, this dotted circle which is shown is actually in the xy plane, okay, and that is this is also xy plane. So, these are actually parallel to each other. So, therefore, if there is a resonance, means the frequency of this matches the frequency of that, then we enter into the resonance condition and the molecule now switches from alpha state to the beta state. So, this is what is shown here. You can see here this arrow which is shown here. Now, in this we are using a very important concept called rotating frame of reference. I would recommend you to actually read this in the books which I have mentioned, because this is a very subtle concept and we try to show it here. So, what is happening is, if you go to this slide again, what is shown here is this circular wave is parallel to this rotational frequency precession, and they, if the frequencies match, we can actually go into a frame of reference in which the frequency and this vector are static, because they are having the same frequency. This is precessing with the same frequency as this precession. So, both are having as if they are looking at each other in a static, they are not moving with respect to each other. So, that is called a rotating frame of reference, and it is a virtual frame. There is not a real rotating frame, it is a virtual frame. We are just, it is like the standard example is, for example, if you are moving, there is a train going at 100 kilometers per hour. If you are standing outside the train, you see the train moving at 100, but if you are inside the train along with the train, for you, or if you are moving another train parallel to this train with same speed, for both of you, each of you are basically static, because both are in the same speed. So, you do not see each other moving at all. So, same thing here, the circular radiation has the same frequency as the precession of the spin which is shown here. So, therefore, we can say that they are static with respect to each other. So, under that condition, the spin now, because this is also a magnetic field. So, if you look back here, what I am applying here is actually a B1, it is also a magnetic field. So, my radiation, again going back a few more slides, this radiation is actually a magnetic field applied. Okay. So, this electromagnetic radiation now starts this, the spin starts rotating around this magnetic field. Okay. So, earlier it was rotating around this B0, that is this axis, but no longer it does that, because we have entered into a rotating frame where this the spinning around this z axis is over. We have stopped that, we are looking into a frame where it is gone to, they are static. Now, in new frame of reference, in the rotating frame, the molecule now starts, or the vector now starts moving around this B1 like a merry-go-round. So, now is a new rotation, now this is a new precession which starts happening, and that is what we exploited to take the spin vector from plus half to minus half. Remember, we want to excite the molecule, we want to go from the plus half to minus half. So, that can happen by simply applying a magnetic field, a rotating magnetic field which takes the spin from plus half to minus half, but this rotating magnetic field has to be synchronized or in resonance with the Larmor precession of this. So, in this next class we will see how this excitation can result in the NMR spectrum, that is using Fourier transform, and that is a spectrum which we always look at when analyzing the data.